Okay, everyone, so now we're finally to our last two types of bonds. This is what's called a metallic bond. Now, it's usually for just pure metals, but we can have different types of metals in here. And what happens, though, is that for metals, the electrons are delocalized. Now, you might remember that we had like those s orbitals, then we had the p orbitals, we also had a d orbital. And as we go up, getting increasing orbital size, subshell size. These are subshells. I always want to say orbitals. They have orbitals inside the subshells. We got more and more electrons. This could have 6, this could have 2, this one could have 10. As we get to metals, these really like pure metals like copper, like iron, they have so many electrons. We've now reached these and they have a whole bunch of valence electrons. So many so that they really just don't even stick with their nucleus. When they're all bonded together, these electrons are more or less an electron cloud. They just flow easily through the metals. And all of these different nuclei, they just kind of sit in the middle of that electron cloud. They're all bonded equally to everything around them. Okay? These are non-directional bonds. They're just happy as long as they're near other pieces of metal. This might also give you an idea of why metals are so good at conducting electricity. Because we have this electron cloud. It's able to easily flow. There's nothing holding those electrons to just one particular atom. No, they're able to easily flow through all of the atoms. And it's because that electricity is able to easily flow through the atoms. The last type we're going to talk about this time, I believe, let me see, is going to be mixed bonding. There it is, secondary bonding. Okay, sorry. Mixed bonding is one other bond type. I missed this one. Sorry, I wasn't even thinking about it. Mixed bonding is the fact that, like I said earlier, that when you have covalent bonds or ionic bonds, it's honestly that there's covalent bonds and they have ionic character. Now they can have almost 100% ionic character as we get further and further apart. So if I put like a 4 here and a 0.7 here, it would be almost 100% ionic character. And we can see that other things like magnesium oxide, well, we said it's an ionic bond, but it honestly has 73.3% ionic character. So it's mostly ionic. It's not quite 100% ionic. And this all just comes from looking at the electronegativities, which we put into this equation. So the further they're separated, the more ionic the bond is, but it's usually a mixture, okay? It's not 100% ionic, it's not 100% covalent. Now, one case where it would be perfectly covalent is if they had the same electronegativity, because you would see then that if they have the same electronegativity, well, then they're going to have, this is going to be 1 minus 1, which will make it 0% ionic. If there's any difference, then it's always going to be some sort of mixture. Okay, now the last type is called secondary bonding. It's a very, very, very weak type of bond. And it arises from the attractive forces between dipoles. And you're like, what's a dipole? Well, think about liquid hydrogen, okay? Liquid hydrogen, it's happy. H2 is stable, other H2 also stable. But these electron clouds, and normally the H's would be in the middle. Let's say that this is in a nuclei. An electron cloud would be equally distributed because of this. However, if I suddenly move a negative charge close to this edge of the electron cloud, it's going to suddenly switch. It's going to be like, oh, the electrons aren't going to like it. And when that happens, well, we're going to have them move over. And so suddenly we have our nuclei, which are closer to one side, which gives it a little bit of a difference in charge. It's more positive on the right than it is on the left. So this is negative, this is the positive side, which means that if I have a second molecule, which has had the similar thing happen, well, guess what? They are now somewhat bonded. Somewhat bonded. So now the negative side is attracted to the positive side that's been induced. Now that's for an induced dipole, which is very, very weak and doesn't last very, very long. However, there's things that are permanent, like hydrogen bonding with water. With water, we have a molecule that looks like this. These small ones right here, these are hydrogen. This is oxygen. And overall, this side is more negative than this side. That's permanent. That's just because of how it is structured. Oxygen stole an electron, so it's negative. This would be 2 minus up here. And each of these lost an electron, which makes them positive. So positive side over here, negative side over here. And what that means is that water molecules will always have that dipole, and it means that they're always going to kind of arrange themselves such they put the negative side of one near the positive side of another. It's why we get those nice ice crystals, or why snowflakes form when it freezes, because they order themselves around this bonding. Hydrogen bonding is also what connects individual strands of polymers in plastics. It's why the polymer strands themselves are very, very strong because of covalent bonds, but the individual bonding, that's what holds our plastic together and keeps it from melting, those are pretty weak. Okay, so this time we learned about metallic bonding. That's between metal atoms, and because they have so many electrons, the electrons are able to easily flow everywhere they want, and the nuclei of the atoms, they just kind of sit in an electron cloud. It's why electricity can flow so well through metals. We then learn about secondary bonding, which is all about the way that either molecules are shaped, as in with water, where we have negative on one side and positive on the other just because of the way it's shaped, or because we had something that was originally perfectly neutral, but because it got scared more or less, I'm using terms like it has emotions, all the electrons ran to one side and the nuclei stayed the same, and so we have an induced dipole that stays for just a little while. This is permanent. This is temporary. So with that, we'll end here, and this is the end. Actually, no, it's not quite the end, but one more lecture, and then we'll be done with chapter 2. Congratulations. We'll be spending a lot more time in this chapter than just these few lecture videos. We got a lot of practicing to do. So I'll see you all soon. Have a wonderful day.